all that processed food cannot be good for you.
I know, but I'm like, it's super disgusting that you just are spraying pudding everywhere.
I could not imagine eating the not a mac and cheese thing. Like, if you want to test if the yellow 5 dye is actually carcinogenic, do the test on them.
Congratulations with the lucky coincidence of lucky numbers. It's like Friday the 13th. So we shouldn't commit fights probably today. Who we are and what are we doing? So it is a physical chemistry class. We are hoping to establish solid bridge from equations to real life and characterization of molecules and materials. We have a boring but powerful arsenal of tools, like equations to predict future and find observables. And we are applying our skills to different objects. And by now, our set of objects that we were able to apply our skills is how many? 2. Yes. Thank you. Which two objects did we succeed to describe? Which two models? Well, maybe you can find more than 2, but at least 2.
Free particle?
Free particle 1 and non-free particle 2. Good. So where is our non-free particle?
In a box.
Yeah. Well, actually, we can tell that we already have infinite number of models because we can tell particle in the box of size 1, particle in the box of size 2 in different dimensions. Of course, it is a relatively poor description of molecules. It will work okay for nanostructures, but you already get some insight into real objects. We have a lot of hard work in the future to approach something more realistic. So next week, maybe on Wednesday, we will start talking about vibrations, motions of nuclei, and how they are affected by quantum nature of the world. What else is administratively important? Let me quickly write something like, if you need equation of motion for the momentum expectation value, and you plug everything into the Heisenberg equation of motion, you will see that from sigma constants, it will be given the derivative over position of potential. So kinetic energy will disappear from there because P and kinetic energy P squared commute, so that they do not leave any traces. And potential does not commute with momentum, and one can see that momentum can be replaced by derivative over x, putting in right constants. And then, if exploring this assignment, you may find this equation useful. I think it is major confuse. I hope to tell a little bit more about homework on Monday. Please, if you just look through and generate questions so that we can speak about homework and make it positive experience for you as much as it was possible. Let's cooperate on this. So what else? This is where we are going. And there is another front, another aspect of our activity, the Wednesday night free will labs. Last Wednesday, we started a new code, which is a little longer than all code we considered before. And what it does, it allows to predict future of any one-dimensional quantum system. We did apply it to the free particle, but to electron in free space. But this time we will modify the potential and describe broad range of systems. This code, I wouldn't say it is answer to all questions in the universe, but it is really useful tool in the framework of this course. So I do not think we can have ambitions above this code. So we will try to apply it to different systems, and there will be 2 sets of presentations until the end of the course. One, when we will split shares, and everyone will explain how this code is working. And it is to be in 2 weeks from now. So I will try to do my homework and create a set of questions, but be prepared to practice democracy probably on Monday. And then there will be 2 lab meetings before we will present how this code is working. Another thing that comes later, it will be also based on this code, so it is not one-time event. Okay, so starting actual meeting. So if someone catches me in the store or calls in the middle of the night and asks, what can you tell about particle in the box? What should I answer? Probably I shouldn't answer anything because it is not appropriate to disturb people in the wrong time. But there should be, well, 2 things that we are expected to know. The Eigen states and eigenenergies, which are, so it is my hardest task for memory, n squared to mass h bar squared, and I don't remember if we found that it should be pi squared, but I think it should to have right dimensions. So this is one-dimensional box, right? And when we met 2 days ago, not in the lab, but here in class, we did cooperate and we made a discovery. We found that there is a way to represent set of energies in the way that will be useful for infinite number of states. We designed a concept of density of states. And we found that for one-dimensional object, the density of states will behave as 1 over square root of energy, right? So, which agrees with our homework and lab assignment that density of states exhibits so-called van Hoff singularities, right? Good. What is the natural direction of thought and exploration if we are staying on this path?
Two-dimensional.
Yes, and then?
3-dimensional.
And then?
Experiment.
Then start some new system, yes. Then experiment. Thank you. So how do these equations modify if you have second dimension? Then we will have more than one quantum numbers. The Eigen state, not writing here. And the energy will depend on two quantum numbers, right? So you do not need to come in class to get this information. This is kind of trivial. Since motion in orthogonal directions are not coupled to each other, since we have one electron, it doesn't interact with anything except the walls. Like if there will be two electrons, they may repel each other, but one is simple, so it goes anywhere at once. And motion along x and y motions along x and y are independent. Therefore, we just solve for them as independent particles and then just multiply. Separation of variables, so the eigenfunction is a product of eigenfunctions for two independent dimensions. Everything is labeled by two indices, and energies also depend on two indices where the size of the box in one and another directions can be different. There is no rule or theorem that they should be equal. How does density of states for two-dimensional objects should look like? Based on your successfully completed homework.
It's the stair step one, isn't it?
Yes, but steps and these events of new features appear because there are some additional degrees of freedom. If we are looking only for pure two dimensions without another degree of freedom, it will be just constant.
Okay.
But you're right that steps, but within some limit it is constant. It would be cool to support this conclusion by something even more solid than your solid homeworks to derive this conclusion. And then we can go to three dimensions as well. So what was our protocol when we met last Wednesday? How did we derive density of states for one dimension?
We did it over like the number of states, or like in respect to the number of states.
So we were drawing a simplified human who moves in one direction, looks behind, and counts how many goes along energy dimension, and counts how many levels are left behind. And this will be number of states. Number of states as function of energy, of threshold. And then we define density of states as number of states per energy interval. Why don't we practice same protocol for different number of dimensions? So I cannot count is it 2 or 3 steps, but draw a walking person, count number of levels behind, express it mathematically, and then take derivative. Make sense? And then, if you will be lucky, we should get something that would coincide with your numerical homework. Right? For 2 dimensions should be flat, and for 3 dimensions should be like square root of energy. Yeah, if it is 3 dimensions, there will be product of 3 independent functions, 3 indices, and energy is 3 components. This is trivial. Okay. So, the walking person looking backwards. No, it's pathetic writing, pathetic drawing. Razor. One other person. Not good. So it's 2 legs going forward.
Andre the Giant.
You don't want to get their knees checked out.
You got the idea. But when we had 1-dimensional box, it was clear where to go. Where this poor person should go if we have 2-dimensional box. Should it go by circles or go like 1 dimension then another dimension?
Wouldn't it make the most sense to just walk like radially outward from the ground state?
Mm-hmm. It's not you. It's just for your quote. Walk radially.
Like which direction should you walk outward? Like what?
Radially from center.
But since you got 2 dimensions, it would make more sense. Yeah, just like radially outward in whatever direction.
From center. I like this idea very much. But radially from center of what?
Your energy states. I mean, the center would be like the ground state energy. For
But
zero energy.
what is 2-dimensional energy? In which space we should walk? Not we, but this symbol.
Choose 1 dimension, so similar as 1-dimensional that we did, and then add the analogous energies at the same time.
Yes, and we can. This is the right direction of thinking. Let me just shape it out and reformulate. So, since we have levels and we can count them by this indices n, x, and y. So, level has index. What's a quantization number in x and y direction? Why don't we consider a discrete space, not a true space, but space of quantum numbers, and put this n x and n y as axis, and then we will walk in, not we, this one, we'll walk in this space. So how this space will be discrete, right? Because we have natural numbers of states. So it should be points. And you already caught me of being pathetic artist. So I knew my weakness and I made a preparation. So what do we have? It is a space of indices. In x and y, right? So the ground state will be when there is a first quantized state along x, first quantized state along y. And idea of London that we should walk from the origin outwards, right? And then count how many states are left behind us. So can we set up the concept of radius in this space? So how far we are from the origin? How far from origin. What should I write here?
The square root of nx squared plus ny squared.
Yes. So we have a concept of distance. And since the space is discrete, probably we cannot immediately apply rigorously infinitesimal increments. Our increments will be a little bigger than infinitesimal. So if we count number of states with radius smaller than threshold, this will be our number of states that we can use for deriving density of states. And we can try to find correlation between this distance from origin and energy of the particle in the box. Right? And then let's walk together in this space, together with drone person. So if one departs from origin to a certain distance, there will be a specific number of states there, right? And the line, this circular line, will correspond to a given energy. We'll go through equation really quick. You'll see it is immediately simple. And as far as we reach to a little bigger distance, we come to a zone of bigger energy, right? And we have an increment between this line and this line. So the number of states that was collected into our repository while we are made the increment from radius 1 to radius 2, or r plus delta r. So the states that are collected in this thin band, thin, how do you say, area, is actually our density of states. So we just need to develop math to count the number of states in this thin band. So this one inside is number of states, here will be density of states. Okay? It is a strategic plan, and now we will shape out tiny details. I was not sure that I will be able to draw circle lines. Here they are. And let's make correspondence between our radius and energy. X and y was constant, and x squared L squared and y squared x y. So let's make an approximation that Lx equals Ly. Then it is much easier. Life becomes easier. And then the energy will be constant, L squared, and x squared plus and y squared. So it will be just some constant times our distance squared, right? So the distance in the space of indices is immediately correlated with energy, right? So we know its distance, we know the energy. And in the opposite direction, if we know the energy, we can find the distance. So R tilde is square root of energy divided by constants. And if needed, we will put all constants as required. We know where to take them, right? So it will be Planck constant, h bar, mass, length, and all stuff. What am I missing? What do we miss together? number of states inside this shape? You know it. You know the number of states inside the shape. You successfully entered the college, the university. You successfully passed the mid-school program. You know the main secret of our civilization. The area inside a circle. Do you know? How much?
R squared.
Pi r squared, yes. So pi r squared is where the success story of math and geometry starts. So this is in the Cartesian, I do not know the history of math, but probably it was from the ancient Egyptians who were cutting the pieces of land, distributing. At least it was first application of measuring the areas. But we are going to look on the area in this crazy space of indices. So in the space of indices, the area will be number of points inside this segment. And if we are looking not on the whole circle, but we have nx and y bigger than 0, right? So from the whole circle, we take how much? Huh?
A quarter?
Yes, we have 1/4. Excellent. So we are ready to give number of states. So NOS will be 1/4 pi r to the square. Right? Yeah, it's a constant that I didn't want to go further. And here's the definition that we already made. So the distance as function of energy. And now we do have number of states. Well, right now it is as function of this threshold radius. 1/4 pi r to the squared. But if we want to plug in definition of r as function of energy, can we do it? What are we going to get?
Use like the square root of energy over the constant.
Well, r is square root of energy. And square of square root?
It's just energy.
Yes. So number of states with energy less than a threshold energy will be some constants that we can work through times the value of this threshold energy. Does it sound convincing? I hope I was doing preparation well and details will be on the next slide. But now, let's practice the definition of density of states, which is DOS is number of states per interval of energy, or derivative over this threshold energy over NOS of this threshold energy. So a derivative of a linear function will be constant. Yes. So whatever this constant was here, you just get constant. So you see, it's not very complicated. We just browsed in crazy space, but actual math was relatively simple. But we got a fundamental result that if you have an instrument or computer code that establishes structure to property relation. So structure is shape, property is density of states. So if you see measured or computed density of states that is flat, you can, oh, I know your system is how many dimensions? Two-dimensional. So what's a scientific technical name for two-dimensional objects?
Planar.
Huh?
Planar.
Planar, but it is something industrially thick. If it is really thin.
Thin films?
Yes. So if you see flat density of states, you say, oh, this system is a thin film. Why thin films are important? Who needs them?
Computers.
Yes. So all processors of computers are flat technology, printed circuits. They, with very good level of truth, they are two-dimensional. So all circuitry of the computers is two-dimensional and is based on thin film technology. And if you like crack the CPU, maybe polish it a little and put it under STM experiment, I bet you will see some flat density of states. Electrochemistry is another way to estimate density of states. It is less precise than scanning tunnel microscopy, and it works only in the vicinity of the gap, but it is also something that allows to find actually states. So it is related to density of states. Okay, so area, constants, number of states, density of states, and actually this constant can be computed. It depends on size of the box. And a constant is what we predict, and here is the steps that you got in your homework, right? So we have a moderate record of success. Agreement between numerical and computation and theoretical approaches. So we together, with collective brainstorming, predicted density of states of all thin films at once. Where should we go next? Yes. So, what do I remember about this course? That we should walk in some crazy spaces. So, which space should we walk in for three-dimensional particle in the box? So it will be nx, ny, and z. And here I didn't prepare points because it will be too hard to watch. But it will be like filling the space with equally offset grid of points, three-dimensional points. And then we need to find an area inside space with a specific distance from the center. Same pattern as we did before. So we define the distance in this space of indices. We establish correlation between this distance and energy. Count number of states inside the which object? Sphere. Divided by factor 8, right? So if you have a spherical pie, then it is very easy to cut on 8 pieces. So the number of indices is 3. Here is energy. This combination, and we assume the distance is, the size of the box is the same. So it is a cubic box. And the and x squared and y squared and z squared will give distance squared. And from this relation, we can define the distance in the space of indices and related to the energy. It will be the same relation as in 2D case, right? So square root of distance is square root of energy times a constant. What were we doing next? Sphere, volume, 1/8, and then distance in which power? Cube. Is there a pi?
There sure is.
In which power?
First.
First. And is there a fraction?
3/4.
Something like this, right? And then we plug, and instead of V, number of states. But R is a square root of energy with constants. Square root means 1/2, power 1/2, right? So the number of states will be whatever constants times e to the power 1/2 and then to the power 3. So 3/2, right? So the further we depart from the center, the amount of levels that is hidden inside this, not hemisphere, but like, I don't know the word for 1/8 of a sphere, but inside this space segment will grow as this power, right? If you want to practice density of states, the dose is derivative over energy of the number of states, right? E to the power 3/2. What's the first derivative of 3/2? So we probably get this 3/2 factor up front, but we don't care because we can put all factors inside this C symbol. And it will be 3/2 minus 1 will be how much?
1/2.
1/2. 1/2 is what? Square root of energy, the threshold energy. So without any concentrations, just in a very relaxed effort, you got a fundamental result that any three-dimensional object, and most of objects are three-dimensional, have universal law for density of states, which is square root of energy. And now you do have a repository of density of states universal laws for one-dimensional, two-dimensional, three-dimensional. Well, you didn't need to come here and listen to me. You did it in your homework years ago. But you can look, if you do an experiment that reveals density of states, you can use this information to analyze what you measure. If you have a friend or colleague who does it, you can, I understand what you're measuring. Based on the shapes of your measured spectra, measured results, I can tell which system you have. So it is not solving of all problems of modern society, but it is a very useful tool. And here is the square root line that we just predicted, and it is what you've got in your homeworks, right? Agrees well. How can we spend the remaining time with pleasure and entertainment? You can, well, this is not very much pleasure, it's just, I repeated the homework myself. So zero-dimensional, the ground state is very offset from zero, at most, right? And then the spectrum is like pikes. And first, here is the one state, and the next one is 3D degenerate, right? Two of the dimensions are in ground, and one is excited. And then swapping the order. Another two are in ground, another is excited. And if we make a little offset of the size of the box, then the degeneracy is a little bit weak. Then if you do have one-dimensional, then we have this, how we describe it, unsymmetric peaks that decreases as 1 over square root of energy. Okay? And then it repeats again when we add offset corresponding to quantization of another dimension. For thin film, it is flat, but due to quantization of another dimension, it will be stairs. And three-dimensional, it will be growing as square root of energy. There is a system that stands out, and we may look for deviations for this word. And system is a flat graphene. It has a very unusual density of states. But for this usual, here is the entertainment, if it will work. No, it is not an entertainment. Do not leave. The announcement of the end of the meeting was fake. The actual completion of the meeting will be soon, but not as soon. Okay, here. I don't know how to comment it, but and if it went too quick, I just decided to have some fun. So if we grow zero-dimensional into this one-dimensional object, you see how they become denser, and it forms this one-Hopf singularities. Then when it starts growing in another dimension, you see formation of this flat. And when it starts growing into the third dimension, you see how naturally it forms this square root of energy. But this is bare practice of the delta functions. E minus E is nx, ny, nz. So I think it is time to congratulate you with successful completion of particle in the box chapter. From now on, there will be one transition meeting when we will just summarize some of our skills and on Monday. And then on Wednesday, we will start talking about quantum nature of vibrations. For Monday, it will be equations in Schrödinger equation in discrete representation. So for a long time we were telling, without much examples, that eigenstates can be formulated either as functions or as vectors. And we will speak more about this connection, about this universality and how equations look like. Finally, end of the meeting. Thanks for stopping by. Have a nice weekend, and looking forward to see you on